Hey, Alex Williams of the New Stack here at DockerCon Europe in Amsterdam with John Willis of Socketplane.io.
Yeah, you bet, bud.
Good to see you. Let's go through this demo. Well, actually, to go through a presentation, right?
Yes, yeah. So to give everybody a little background, we were talking yesterday, me and Alex, about just what I'm up to in my new company, and I think hopefully I can talk about that at a different point. You know, we're doing SDN for Docker and Socketplane.io, and hopefully you guys know me as Botchgloop on Twitter to get a hold of me if you have more questions. But I really I was trying to explain to Alex what my vision of how SDN is evolving and what are some of the good things, what are some bad things, and he was like, dude, we should do that as a hangout, as a presentation.
Yeah.
Because I've been real lazy about writing blog articles over the last couple of years.
That's a good way to do it.
Yeah, so good. So yeah, so I have this presentation I've done called SDN, the Elephant in the Room. Actually, jokingly, I did this at a Lisa conference in a 40-minute presentation, and last week at the DevOps Days Ignite, I did it as a 5-minute presentation.
Oh, nice.
Same presentation, same amount of slides. So I think what I'll be able to do here, though, is try to hit it in around 10 or 12 minutes, maybe 15 if we have some really cool questions.
Okay, great.
So, this first slide is really it's actually a ripoff from Little Idea. Andrew Schaefer, who did this when DevOps first came out, which, the blind man and the elephant, and everybody's trying, and his capture was, what is DevOps, right? And I thought, when I started thinking about DevOps and networking and all this stuff, I thought we have a similar problem here with this title called SDN. Like, what is SDN? Some people think it's the switching fabric, some people think it's the virtual switching, all across the board. So kind of opening up with, like, it's an overloaded term that a lot of people, in particular vendors, very much like DevOps, very much like cloud, people kind of glom onto and kind of steal their version of it. And of course, I'm a vendor, so you're going to get my version of it too. So, but there's some really good background here. There's a Scott Shanker video. He was one of the original Nicira guys. And it's, to me, one of the best videos describing SDN. And what he does is he's a Berkeley guy who goes to Stanford, where SDN was invented in Martin Casado and all that, and he basically does a department-wide presentation on SDN, it's brilliant, and he talks about why we did SDN, and what he said was, it was really cool. Like, all right, let's get some why SDN. Real simple. Networks are hard to manage. No disagreement. Networks are hard to evolve. Right? The way we've written router protocols and stuff have been very effective, but not very malleable. Mm-hmm. And then third, last but not least, they're hard to understand. Like, our true network architecture and logic designs are geniuses, right? And so the horses in the unicorn horse analogy just struggle with how to deal with networks. And so we said, you put those three together, there has to be a solution. And so SDN was this kind of idea that, if you look at this next slide, at the end of the day, the pragmatic definition of SDN is this. Simply, what somebody would say, it's the decoupling of the control plane and the data plane. Mm-hmm. So network devices, switch, router, we're going to just kind of play with the switch idea for now, are made up of 3 planes. So if you look at the left-hand side of the slide, right, made up of management plane, control plane, and data plane. The control plane is the distributed brains of how networks work. Typically, pre-SDN, decided through distributed technologies like things like BGP, OSPF, MLPS, different types of really clever distributed routing protocols. Those things get spread out to all these different switches, if you will, and that becomes the distributed and the true eventual consistent brain of how networks. That's brilliant. Works well. It's how the internet works. Right. The problem was, it's extremely hard for a company that has 40,000, 50,000 network devices that have to keep all the metadata in line to make that happen, because the metadata to do that stuff is kind of a black art, right?
How much power do you have?
Probably enough.
No. I'm running down on almost empty.
Okay, there we go. Let's switch, and then if I start getting messages,
we'll go back and forth if we need to.
So that's the control plane. The problem was, in Shanker's definition, there was no really good abstractions for that. Now, data plane is really just pack it in, pack it out, like wire speed, like this is the meat of what a switch does or a network device does. So the idea of SDN was to make the data plane more malleable for the horses, if you will, by making this kind of new model of how you update data planes by separating the control plane off of the device to some infrastructure. So you have things like Nasira's NSX and Open Daylight. These are models of this separation of control plane. And so that
Plum Grid.
Yeah, Plum Grid is another example. Nuage and and Socketplane now is a model for that for Docker containers, right? So, and the idea is that you are making the data plane programmable in a different mechanism than a very brilliant distributed model, right? So that, in a sense, now again, what is SDN? Well, this vendor will say it's this, that. The pragmatic definition, if you go by Scott Shanker and definition, they would say it's simply the decoupling of the control plane from the data plane. I would say it's making the data plane more malleable and programmable. Now, the thing is, though, to look at where we were, where we went, and where we probably should go, right? And this is what we were talking about yesterday. Is you look at like node distribution. So again, we're talking about how network devices get managed. We started off in a world that was distributed. So if we go here, the classic pre-SDN was a distributed model, like we saw on that left-hand side. Basically, all nodes got eventually consistently updated through router protocols, things like BGP, OSPF, stuff like that, and that's how the world worked, and it works very well, and it's the reason why we're able to use the internet so efficiently today. And then we went to this kind of, I will say it might be called by some, throw the baby out with the bathwater model of a centralized, like all the really great things about that, screw that, it's too hard, let's go this new way. Right, which is your classic SDN model, right? And in that case, it is kind of a forwarded population, a control plane that now is separated. Different vendors have different models of how they manage that, but it's some type of centralized store that keeps all the data planes updated through a programmable model. I got more examples of this in a minute. But the problem was we threw the baby out the bathwater. There were certain things that router protocols and true model did really well, and the things that didn't do well. And so, the joke is, I stole this slide from one of my business partners, basically our beloved kittens and cat pictures, right? Like distributed protocols, we should be thankful. I actually I don't really like cats, I'm on the record, so I actually am not thankful for things like BGP and OSPF because I get cat pictures from all sorts of people all the time. But at the end of the day, the general population's beloved fascination with cat pictures is solved by distributed protocols. So what has been emerging, and some of the vendors that do this, and my team is particularly because they worked on Open Daylight for a while, is they've kind of come up with this kind of decentralized model. There's the SDN book by O'Reilly actually has a good explanation. It is, we actually internally been calling it kind of retro SDN, which is now kind of a little bit of both. Nuage is actually a good example of a product that does this well. And in some ways, we think we're kind of taking some of the best of NSX in Socketplane and the best of Nuage to do it for containers, right? So this is a model where you have central points of control for lots of things, and then you're using the distributed protocol stuff for others. Like, so in our example, if you're doing container-to-container stuff, like if you just want to create logical network virtualization between certain containers spread out, like 2 on this box, 1 on this box, 3 on this box, and then another logical network for other containers on those same boxes, then you might be better suited to use a classic router protocol like a BGP for that, as opposed to a control plane that programs down, because this stuff works. Now, for other stuff that SDN does really well, which I'll talk about a little bit, like the VMware calls microsegmentation, like things that you can inlay services in the data plane manipulation, and I'll go into that in a little more detail. That actually works really well from a control plane theorem. So our approach, and we're not the only ones doing this, I said Nuage is a good example, where you try to take the best of both worlds and you solve some problems with the kind of SDN purist model, and you solve some problems with the old, and this has been described as a decentralized model. And so what we're talking about here is, when I talk about the control plane, data plane, what we're talking about is the ability to program data planes, that packet in, packet out stuff, right? And how do you get that done, and when is it necessary to create kind of human-defined logic as opposed to computer scientist-designed router protocol logic. Does that make sense?
Yep.
Yeah. So, and again, that's a core of what SDN is trying to do, right? Is how do I make this programmable for the horses, right? And so one of the more prominent approaches, not the only approach, is a protocol called OpenFlow, right? And it is actually kind of used mainly by Nicira, a lot of the vendors, Open Daylight, right? And it's just an idea where the control plane, you build this kind of match instruction counter logic, and that gets populated down to the data plane. So what you wind up seeing things like this, where you'll have matching tables actually in the data plane. They call them flow tables, where a packet comes in and it just basically goes through the table. Is it protocol TCP? Is the IP destination 1.1.20/32? Is it port 80? Go out that port.
Right.
And so this starts creating some kind of potential magic of dynamic decision making at
the tables.
And more importantly, that those tables are in the kernel space. This is what one of my cohorts calls the fast plane.
So do the tables actually have then the logic built in?
Yes. So and I have a diagram for that too, right? They're basically what they're called is flow tables, and they're really kind of sophisticated matching, and there's actually some wildcard and stuff like that creates like, all right, looking at the packets and doing this matching, and this goes there. Oh, next one, bam, it goes here. But so the point, going back, remember earlier I said VMware calls this microsegmentation, and I might have maybe said Microsoft. I do that sometimes. So if you heard me earlier say Microsoft does it, I was wrong. I meant to say VMware. I don't know why I confused those two guys. But so what do you do? What is that microsegmentation or service chaining is sometimes called? It's the ability to do things like isolation, segmentation, and what VMware would kind of categorize as advanced segmentation. Isolation are basically tunnels. So like VLANs are an abstraction to do kind of multi-tenancy on a switch, right? Like I can make a switch look like multiple tenants. But the problem was that's very coupled to the hardware, right? Or even the virtual switch fabric. Very much like cloud or compute. Like virtualization was a good attempt as a first-order abstraction to sort of kind of virtualize a physical box.
Right.
Oh, I could put 10 on here, I could put 20 here,
right.
But I still had this tight coupling with the hardware. And then we moved to cloud, right?
It's kind of expensive.
Right, and when we got to cloud, we had a kind of second-order abstraction where we allowed us to completely decouple the requester's resource of a compute from where it wound up on. Well, in a broad sense, that's what an overlay is, right? An overlay allows you to kind of, and a VXLAN is like an extended LAN, right? Now I can create this logical network that has no coupling to any physical switch. Right, and they classically call these overlays. So now I can logically create these. I can call, and this is basically network virtualization definition at its core. The ability to create these virtual networks that I can change on the fly. I don't ever have to update per se any switch configuration files because it's all being done through a manipulation of control plane down to the data plane, and the data flows are determining. Oh, yeah, I see this guy. I know who he is. He's part of that logical network back. And the three, VXLAN is one of the most popular VANs. GRE is used a lot in OpenStack. But so again, back to what do you do with this data plane manipulation? One, possible isolation, overlays. Very popular. Create multiple logical networks. They can be changed, moved, malleable. The second is you can do this segmentation. And I think this is where it gets really exciting. And this is why I'm really excited about Socketplane and containers, because I can start moving service features into the data plane manipulation. So I can do kind of firewalling in the data flow process, right? So instead of like bouncing out to IP tables to find out what I need to do, I could alternatively, possibly, go ahead and start putting that logic in that programmable data flow. I can also do QoS. I can do load balancing, and this is all the promise of SDN. So if you read anything from like Nuage, PlumGrid, or particularly NSX, they have probably the best documentation on this concept. You'll see that they're promoting this idea that I may not have to run like 10 HA proxies, or I can actually start putting that programmable logic inside of the data plane. And then it goes on and on. Like it could be traffic redirection. Another thing I get fascinating, being a DevOps guy, is telemetry.
Back to this whole idea of flow control. Really.
Exactly. And so here's an important point, though. Remember earlier I said, like, we think of this idea of a retro SDN, right? Like there was the kind of original distributed, and then there was the centralized, and then there's kind of so a good example of the way we're thinking about this is if I'm doing container to container stuff, I probably won't do that logic in the flow tables. I'll do that through doing dynamic routing with BGP. But if I want my customer to have QoS or a possible load balancer logically built in the data plane or firewalling capability, then I will do that from a control plane data plane manipulation. So that becomes that best of both worlds possible solution. There's some interesting things about firewalls. Like today, it's a little difficult to do stateful firewall, which is something IP tables for the really intelligent guys who listen, the gals and girls. Just want to be clear, there are some really clever things happening in OpenVSwitch that are going to make IP tables and OpenVSwitch on par, probably by the end of this year. So here's the thing, right? What I don't want to do, and particularly when I go, here's another thing. The reason I get excited about what we're doing is I think the potential problem of containers, which is a great opportunity, is we're going to see an order of magnitude of scale. Right? I think a host for some provider that's over provisioned, maybe at 200 VMs per box, could be 2,000.
Martin Mikos compared it to the LAMP stack when you started putting databases on it, and then you got to the point where you need to put 1,000 databases, on these LAMP stacks.
Yeah, no, I think we're
now you're like 1,000 containers is nothing but 1 million, 1 billion.
I think an order of magnitude is being gracious, right?
Yeah.
And so I've heard stories of some cloud providers over provisioning VMs 20 per core. To think about a 64-core host, I mean, start adding numbers. We're talking about a lot of. So we got a couple of problems here, right? We're going to have a lot of containers on a physical host.
Right.
But there's another order of magnitude problem coming. It's not just the magnitude of how many we're going to have. Like today, if we're running 1,000 on one box, tomorrow we run 10,000 or 100,000 on that box, right? That's a problem. But there's a bigger problem because we start talking about microservices and a new type of way to do compute. And I don't want to go too crazy here, but like you add data gravity, you add IoT, you add containers. I think it's very clear to me and to a lot of people who discuss this that we might see an order of magnitude shrinkage in the time that compute resources live. Mm-hmm. Right? So like we think this came up yesterday in one of the presentations. Like even in the most advanced shops, compute resources stick around for hours. Most cases, sometimes weeks. Still, even in cloud infrastructures, they're around for a while. I think when we start re-architecting design patterns from microservices, I think the norm is going to be maybe compute in minutes and seconds being more likely for something to exist.
So what does that mean?
So the impact to that, or do you mean what does it mean?
So what does it mean? Like when you're saying then the compute is going to be just consolidated.
I think that what you're going to see in a microservice architecture, so if you take the data gravity, I know I'm overloading concepts and we're going to totally blow that 12-minute thing, but probably worth it. If you think about Dave McCrory's data gravity, if you hadn't seen it, datagravity.org, right? Like we're going to have
the data.
You don't move the data. So our classic was that we basically move data compute, very simplistic, very mathematical definitions of it that I'm not going to get into. Explanation of data gravity is we're going to move compute to data.
Right.
So if we think about large clusters of data and how I might think about how I process in a microservices and container world, I may just do these kind of concepts of swarm a bunch of compute, stop, go swarm here, go swarm here. I mean, that's just one pattern. I can think of many patterns where compute resources may just live. In fact, I just heard yesterday there was a presentation about Adrian Kokov talked about the AWS Lambda. Like holy crap, right? Like so, yeah. I mean, this world of up and down is going to change not only our world of how many, but I think our OpEx world of going up and down. And so you better be prepared for a world that better be in the fast plane all the time. So this picture right now, this movie has a shitty ending, is a world where you either live, most of your work is in the fast plane, or you're doing this trombone effect to the slow plane. And I don't know at the end of the day who's right, who's wrong, when you're going to use HTTP. I'm not suggesting HTTP proxy is going away, or not suggesting that IP tables is going away. I'm just saying the OpEx world of those models might get tricky, where A, scale is going to, and the ephemeral nature of compute is going to get more ephemeral than ever.
Right.
Right. So, which leads me into the most popular open source virtual switching fabric out there, which is called vSwitch. And this is the thing I'm probably most passionate about right now these days. And this really kind of, and excuse me to me being the neophyte, that if there are other prominent ones, the two that I know of is there's vSwitch from VMware, which is proprietary, and there's OpenVSwitch.
Right.
OpenVSwitch is the most prominent one used for Cloud Stack, OpenStack, most of those models. Obviously, vSwitch is used for vSphere, vCloud.
Right.
This is what OpenVSwitch. A lot of people don't really understand. Going back to that elephant in the room, right? Like there goes so many pieces. I've covered a couple of them. OpenFlow, what that is. It's a protocol. OpenVSwitch is actually a physical piece of software that does virtual switching, no hardware required. Right? You put this virtual switch on a box, and it acts like a switch, even though it's not really a physical switch like a Cisco or an Arista. And so, just in brevity, there's a great article about here, a couple of PowerPoints. It's made up of a couple of components. There's what they call the OVSDB server, which is basically its management interface. OpenVSwitch is basically the kind of flow table manager, and my partner Brent Salisbury says the greatest thing Martin Casado ever did was get OpenVSwitch into the Linux kernel. So like of everything he did, this was, in my friend Brent's opinion, the most brilliant thing he did. I'm sure him and his team get all the credit, but it is the fast path there is in the kernel, and you can look at the different flows, when it uses OpenFlow, when it uses Netlink. So that's basically OpenVSwitch. And here's the thing about OpenVSwitch, right? Like I'm going to do a lot more presentations and talking, and maybe I'll get on lazy and write a whole article for you on OpenVSwitch. But a lot of people I talk to about OpenVSwitch, they talk about, oh, I tried OpenVSwitch, it was, oh. So the problem is, almost everybody I know who says that were at 1.9. And at 1.9, it was basically single-threaded. It didn't have this thing called megaflows. If you search out the OpenStack Paris Summit, the Rackspace guys did a how to manage OpenVSwitch at scale. I don't know if that's the exact name, but it's easy to find, right? Just look Rackspace, presentations, Paris Summit. And I stole this, except for the last bullet item, I stole this completely from them. They said in their presentation, prior to 1.1, OpenVSwitch's dark age is at 1.1 or above. They added what they call megaflows, and then they've also added multi-threaded implementation. They say that at 2.1 right now they have no issues, and they run OpenVSwitch at the core. They call it ludicrous speed. Here's the thing: you start adding in some of the offload accelerators like Intel and other proprietary stuff on this kind of new, which is now a host. It's not a physical switch. Here's the thing: the new edge is a host. It used to be the new edge was a top-of-rack switch, and then you had all your hosts into it. The new edge, either it's a virtualization, and certainly with containers, is actually a host, which is going to be an x86 host, which is actually going to have a virtual switch fabric on it. And so how do you get your accelerators that you got in your old switches? I think Intel's going to solve this problem. With DBDK, deep packet inspection, NIC cards that accelerate overlays like VXLAN and stuff like that. Right. So you start adding that, and then playing the joke on if you've seen Spaceballs, right? It's with accelerators, OpenVSwitch will go to plaid. So anyway, and that was, I think, the last slide, which is, there are some really interesting, and we're playing with this stuff, some cool offload accelerators, network adapters, some things for DBK acceleration and whatnot. So anyway, I think that's all I have here. And again, my intent was here to I think there's a lot of confusion about AES SDN, a lot of confusion about what's the difference between vSwitch and OpenFlow and SDN, and why should I even care? And half the people are saying it's the greatest thing since sliced bread right, or the other people that are saying it's a bunch of baloney,
But
right?
if you think of it in the context of this container
Well,
issue, then you can start to, I think then you can start to provide, there's less abstraction about this concept, for people, because now they think, well, what are we going to do if we have billions of containers and and it takes milliseconds for the
to come up and then come down,
Yeah.
right? I mean, I was talking to my buddy Patrick DeBar this morning. All this cool stuff with Swarm and stuff, right? That was
Yeah.
announced yesterday, and like that's cool. But like one of the things he's doing is running a bunch of Docker stuff. How do you deallocate off of boxes? And what's the time consuming? Again, there's just a lot of OpEx issues that are just going to be more complicated in a container world. Because again, there's going to be more of them. You're going to treat them. You're going to architect your design of your applications differently.
It's fascinating because it brings the element of time actually into the programming itself. I mean, there's a
it for the first time. So it's funny. Back in the early cloud days, right? And me and both of you were in this discussion very early on. And I mean, there was a significant order of magnitude time thing that made it a big difference, right? Like we went from the 2 week, or I say it's 8. People say 8 weeks to get a compute resource.
Right.
But keep it consistent. Let's say it went from 8 weeks to 8 minutes, right? Like give or take. Some providers faster, slower. How you build out chef stuff, whatever. When the customer got their delivered thing, let's just say it was 8 minutes. So we went from somebody requesting compute resources from 8 weeks to 8 minutes, and it changed everything. The last 5 years have been insanely changing.
Yeah.
I will say that because when you start looking at containers, and again, just to keep numbers consistent, we're going to go to 8 minutes to 8 seconds.
Yeah.
And really, most people say it's about 2 seconds to converge a server structure with a container. It's about 500 milliseconds to start it. But let's just say 8 seconds. So we're going to go through another, as significant as our world has changed in the last 5 years, because of that 8 weeks to 8 minutes, I say we'll have equal, not even a more significant impact on the way we do things from 8 minutes to 8 seconds. And I think therein, me being an ops guy for 35 years, this is a tremendous opportunity to get ahead of the curve on a potential OpEx nightmare.
Well, John, thank you for sharing this. We should talk more about the container complexities with networking. It's a real weak spot, that I'm hearing is going to need to be really resolved, but it's
and it's not a negative, right? I mean,
it's not a negative at all.
Docker's 20 months old, right?
Yeah.
Like, so to be even this fast on a discussion and the maturity level of discussions that we're having in a 20-month-old project is absolutely insane.
Which says a lot.
Says a lot. Yeah. So it just means there's a lot of work to be done.
Yeah. Well, good. Well, great. Well, thanks a lot.
Sure. No, it was a blast.